Okay, thank you. This is Zezhong Wang. So glad to have the chance to share my work. The title is Prior Omission of Dissimilar Source Domains for Cost-Effective Few-Shot Learning. Okay, now let's begin. In this work, few-shot natural language understanding is the main task, as known as the few-shot NLU. Like other few-shot learning tasks, few-shot NLU faces the same problem of limited level data. This is the first challenge, as known as low resources, we try to solve in this work. As our method is based on transfer learning, we also found the phenomena of negative knowledge transfer during the training. So negative knowledge transfer is the second challenge solved in its work. For the low resources problem, we propose a transfer learning-based model, shared private network, to learn a level representation with limited annotations to improve the performance on few-shot NLU tasks. And for the negative knowledge transfer problem, we design a data selection method that select data before transfer learning to avoid negative knowledge transfer. Before going through the main idea, I'd like to introduce the task first. NLU is a task to recognize predefined semantic slots from sentences, and usually is regarded as a sequence leveling problem. Please see this example. Given a sentence, will it rain in Hong Kong next Monday? The model is expected to recognize the city and time from the sentence. Therefore, it is a sequence labeling task that assigns each word a label following the BIO annotation schema. Okay, the label O represents the other words. Label O represents the other words. That is not a semantic slot. And the label with B tag means that the words is the beginning of a semantic slot. For example, the B city and also the B time. And the label with I tag means that the word is inside the slot. For example, the ICT and the I time. So few-shot means that there is less label data in the target domain. Okay. The motivation of few-shot NLU task is straightforward. There are almost infinite long-tail domain in the real world. So it is nearly impossible to annotate sufficient data for each domain. This picture shows this point. Some domains are common and some domains maybe not common. Okay. For example, a book restaurant is a common domain, as many people usually call to book a restaurant, right? So book a restaurant may be a common domain. And there are also many uncommon domains. We cannot get and label sufficient data for all of them. For example, add to playlist maybe is an uncommon domain. So as few people do this via dialogue. There are also many other uncommon domains like search creative work, get weather, play music, read book, and search screening event. We cannot get enough data and label them to formulate training set for the supervised learning. That's the few-shot NLU task motivation. Okay. So in this work, low resources is the first challenge we should solve. Supervised learning is not a good choice when the level data are limited. This kind of method overfit easily under the few-shot setting. And therefore, transfer learning is proposed to handle few-shot tasks. In one word, transfer learning is a method that transfers the knowledge learned from the source domains to target domains. Suppose we have sufficient level data on the some domains, we call them source domains. Okay, and a domain with less level data, we call them target domain. However, there is also another challenge, negative knowledge transfer, which means that leveraging source domain knowledge reduces the learning performance in the target domain. So in this work, we firstly overcome the negative knowledge transfer and then solve the few-shot problem. Okay, in the following section, I will introduce the negative knowledge transfer And our solution, a domain selection strategy. Before going through the solution, we should prove the negative knowledge transfer exactly exists in the few-shot NLU task. The proof is easy. We can run experiments several times, keeping all hyperparameters the same, except the source domain for training, and find one experiment that uses less training domains but achieve better results. Okay, here we skip the tedious experiment setting like the dataset, models, and etc. We only focus on the selection of training domains. There are 6 domains we can choose. We select one for testing and one for evaluation, and randomly select 1 or 2 or 3 or 4 domains from the left 4 domains to train a model. And then evaluate and record the results on the test domain. The results are shown in the red. The horizontal axis is the number of the source domains for training, and the vertical axis is the F1 score, the performance. Okay. Overall, with more training domains, the performance would be better. However, comparing the maximum value is obviously the training with 3 source domains. This point outperforms training with 4 source domains. That means there is at least one experiment trained with 3 domains get better results than all experiments trained with 4 domains. So in this way, we successfully observe the phenomena that better results with less training data. Okay. We propose a domain selection strategy to solve the problem of negative knowledge transfer. We assume that the knowledge from dissimilar source domain is redundant and can be considered noise. Therefore, we select source domains for transfer learning rather than use data from all domains to avoid negative knowledge transfer. But there are still questions. How to, for a target domain, how to figure out the dissimilar source domains, or how to define the similarity between domains. In this work, we investigate several text similarity. There are also 2 conditions. Firstly, there are few label data on the target domain, so we cannot compare the class distributions among different domains. And secondly, domain selection should be done before training. That means we should not use model to evaluate data one by one. This is also for the efficiency. We take following 3 similarity function. That is target vocabulary covered, calculate the vocabulary overlap between 2 domains. Okay, and the TF-IDF similarity, TIS, considering each domain as a large document and calculating their TF-IDF feature vector, the cosine similarity between 2 TF-IDF vectors are regarded as a similarity between 2 domains. And also the label overlap, LO. Though we cannot have too much label data on the target domain, we still have few samples. For example, 5 label data for 5-shot learning. So we can know the type of label in the target domain. Therefore, we can get the label overlap between 2 domains. These 3 functions have their own advantages, so we combine them together and get a combined similarity function. The best practice of the weight of each similarity function is shown here. Naturally, we will ask which similarity is better, or what kind of similarity function is good indicator for select domain. Here, we give the answer. The indicator should output a score that can reflect how fit are these source data for transferring knowledge to the target. Ideally, the indicator score behaves linearly with the performance so that a higher indicator score can lead to better performance. In this way, the group of source domain with highest indicator score can be selected as a best choice for training. We further visualize the relation between the performance with the similarity score. Compare the combined similarity with the TVC. For TVC, the performance generally positive correlates with the similarity score. However, the precision is poor. Okay. By comparison, there is an apparent positive linear correlation between combined similarity and the performance in the red picture. Okay. After domain selection, let's see my model, a shared private network. This picture shows our model structure. Let's see the process step by step. Okay. Few-shot learning provides few label sample. We call the site of the sample as support site. We firstly encode all of the sample one by one via a pre-trained language model. Here we use the bird. After that, we get a word embedding for each token, and we select the token with semantic label. For example, the word New York. Okay, and put them into a shared layer and a private layer separately. We hope the shared layer can further extract shared features from the words in the same class. By contrast, the private layer should extract private feature from the words. I'd like to give an example here. If we replace Hong Kong with New York, such as book a ticket from New York to London tomorrow night, we can see the sentence still makes sense, right? That's because Hong Kong and New York are two places, so they should have some same semantic feature. We call them shared feature. On the other hand, although the sentence is without any grammatical mistakes, after phrase replacing, the meaning has been changed. This is due to private information carried by the word. We call them private feature. Initially, the words in the same class should have the same shared feature. We use a contrastive loss here to make the shared feature from the same class close to each other and make them from the different class far apart. By contrast, the private feature should be diverse, even though they belong to the same class. We use a negative log cosine similarity as a constraint to make the private feature with high divergence. There is still an extra condition that shared and private features of a word should not overlap. Here, we introduce the orthogonal constraint to force the shared feature independent of the private features. Okay, finally, we take the mean vector of the shared embeddings, which belongs to this class as a label embedding. The red part shows the predict process. Given a labeled sentence, it will be first sent to the same bird to get the word embedding, and then go through the shared layer to get the shared feature. Then we calculate the cosine similarity between each shared feature with the label embedding. After normalized, the similarity can consider as the prediction distribution, so that finish the predict.
Sorry,
okay.
You're a bit out of time.
Okay.
Your time has expired. If you can shortly go to conclusions.
Okay. Okay.
Sorry about that. It's very interesting, but we have to keep the time.
Okay. Let's see the results directly. SPNet is our method, and SPNet plus domain selection is also our model with the domain selection. We can say on all of the domains, our method achieved the best results. Okay, no matter on one shot or 5 shots. And this is also a comparison between different similarity function. The green one is a combined similarity function. We can say it's also the best one on the top of all of other similarity function. Okay, that's all of my presentation. Thank you.